So we were talking about how frictions affect the estimation of labor supply elasticities, and I was going through this econometrica paper of mine from this year, where, just to briefly review, it's a standard labor supply model where you've got heterogeneous individuals who, in the lecture, we're going to assume have quasi-linear utility functions, so there are no income effects. And we generate these demand functions, so we're thinking about demand instead of labor supply. Agent I's optimal demand for good X is given by this demand function, which we take logs and get this expression here. And then, as we talked about, if you assume that tastes are orthogonal to the price variation, then the structural elasticity is identified by the difference in average log demand divided by the log change in prices, right? So the observed impact of a price change on demand identifies the structural parameter epsilon of the utility function, which is this curvature parameter that controls the elasticity of interest. And then we talked about a couple examples of frictions that would destroy that relationship. So for instance, if there are adjustment costs, then the observed elasticity that you estimate from a price increase in the data, that is what the econometrician estimates, call that epsilon hat, is no longer going to equal epsilon, the parameter, the target parameter you're trying to identify. And in this particular example, epsilon hat ends up being attenuated relative to epsilon. It's smaller than epsilon, but you can come up with various other examples where it might be larger than epsilon and so forth, as we talked about at the very beginning of the labor supply section of the class. So the question is, how do you go from estimates of epsilon hat, which is what we're able to identify in the data typically, to the epsilon parameter that might control behavior in the long run, because these kinds of frictions like adjustment costs and attention perhaps become less relevant in the long run. Okay? So the way I make progress on that in this paper, and I think it helps you think about what frictions do more generally, is restrict the size of frictions in a specific way by requiring that the utility loss is less than some exogenously specified threshold. So the idea is that many standard models of frictions, like dynamic models of adjustment costs, are going to generate this type of behavior where you might deviate from the optimum, but you won't deviate too far. And the logic is, so to take a specific example, like suppose the adjustment cost is 1% of consumption, you will never choose a level of consumption that generates a utility loss of more than 2% of consumption, because you can always switch to the optimal level of consumption and switch back to where you were before by paying the adjustment cost twice. So there's no possible way, no matter what the parameters of the model are, that you will stray beyond that 2% threshold. So that's why this turns out to be like a good restriction, that no matter what all the complicated structure of the model looks like, you're going to satisfy this condition. That might also be true for other types of models of frictions, like inattention, if you think that you pay attention to things that are important but might neglect things that are not that important from a utility point of view. So this type of idea has precedence in the macroeconomics literature, the near rationality literature going back to Akerlof and Yellen and others. So basically the way to think about what this paper does is takes that kind of assumption and thinks about its implications for empirical estimation and identification rather than macro questions like inflation dynamics and so forth. Okay, so specifically what we're going to require is that the maximum utility you can attain minus the utility you actually attain is less than some fraction of the expenditure on the good. So this is just a way, the delta parameter here is a way to scale the size of the friction. We're scaling it as a fraction of the expenditure on the good. That's just a normalization. That doesn't actually matter.
How restricted is that assumption that it's sort of proportional? I mean, you can imagine that there are sort of other, you could have frictions be like,
a number, like,
fixed amount.
absolutely. So let me be clear on what this is. I could have just written this as less than some delta, like some number, and everything that I'm going to show you is going to go through the same way. The reason I like to write it in this way is that it's more intuitive to think about maybe magnitudes of frictions, I think, from this perspective. So if we're talking about different types of problems, like choosing labor supply or choosing consumption of a car, it's hard to think about, should I allow a friction of $50, $1,000, $20,000? It's a little bit easier, I think, to say, 1% of the expenditure on the good, 5%. But like I say, that's just a scaling. I'm not, in the results, actually taking advantage of this proportionality. That's not important for what I'm doing. You could just have a number there, and you would get formulas in terms of that number. But then you'd have to have an intuition about how big that number is. OK, so as we talked about before, if you specify a delta, that's going to map a given price to a choice set rather than a single point, right? So I showed you this figure before where this is the utility maximizing point, and what we're going to require is that you pick a point near that optimum, so that's going to generate that choice set. And so then, as we also discussed, the dashed blue line here is the structural elasticity that we would identify if there were no frictions, but all we're requiring is that you pick points within these sets at those two levels, and as we talked about, that generates many different potential responses to this price change, which is precisely the problem that I think this literature confronts. So now what we're going to do is say, we're going to invert that problem and ask, suppose you're able to empirically estimate an elasticity. What does that mean for what the slope of the blue line looks like, which is really what we're trying to identify. Okay, so specifically what I do in this paper is derive bounds on epsilon given estimates of epsilon hat. And before describing exactly how that works, I just wanted to do a brief segue to talk about what this technique is representative of, a broader segment of the literature in econometrics that is increasingly influential. So this approach of bounding the elasticity is, you can think of it as sort of an example of the modern econometrics literature on what's called partial identification, or also called set identification or moment inequalities in I/O. Those of you who are taking I/O class would have heard that term. So the idea of set identification instead of point identification goes back to a seminal paper by Mansky in '93, and there's a very nice review by Ellie Tamer in the recent annual review that talks about this literature. So this is quite different from the typical like applied microeconometrics that you learn about. So let me just say a word on what this is. So the main concept of the partial identification literature is to avoid making strong and untestable assumptions about the data generating process. That's the way Mansky and Tamer and others have been thinking about it. So instead of making a specific assumption about the way in which the data is generated, you derive non-parametric bounds on parameters under worst case scenarios. So you can see why this fits very much like in terms of methodological style with the type of stuff we've been talking about in this class, which is all about reducing the number of assumptions that you're making in order to derive conclusions, right? And this is like the empirical analog of that. So here's the classic example that I think makes it very easy to understand what this is about. And then the econometrics get much more complicated, but the idea basically boils down to this. Suppose you have a case where you have missing data. Okay, so common problem, especially in survey data. Now, to make this simple, suppose you have a binary outcome. So the outcome is either 0 or 1 as the result of some treatment. Traditionally, the way you proceed in that situation is that you make some assumption about the nature of the missing data. Like let's say for half the, or like a third of the people, you don't assume whether they're working or not because that data is just not reported. And so usually what you do is let's assume that the people who are missing are similar to the people on whom I have data. So that's a missing at random assumption. And then I can estimate a treatment effect on the people for whom I have data, and that's going to capture the population effect. But that relies on a super strong assumption that the missing data is similar to the data that you actually have, which clearly need not be the case, and is typically not the case in practice, because missing data is not occurring randomly. It's because the types of people who don't respond to surveys maybe are the ones who are not working, who are moving around. There are going to be all kinds of features of that particular set of data. So Mansky's insight, which is straightforward in this example, is that it's easy to derive bounds by taking extreme cases on what the missing data might look like. So take the case of, let's say the simplest possible example, I just want to estimate the mean employment rate in the economy. And suppose 20% of the people have missing data. I can assume those 20% are all employed or those 20% are all unemployed. And you can see how I can get a set for the potential mean employment rates in the economy, right? That is completely non-parametric. No matter what the nature of the missing data looks like, you know that set is going to contain the mean that you're trying to estimate. Now you can extend that to think about estimating a treatment effect with binary outcomes, again assuming that the data is all of the worst possible case. So how does it work with the treatment effects? You kind of assume the worst case scenarios where everybody in the treatment group is at one end and everybody in the control group's at the other end, or flip it around, and then you're going to get the bounds, right? So that technique can be applied in many, many contexts. So like in I/O, where you don't have all the moments that you're trying to identify in a structural model, the type of work that Ariel Pecos and others are doing now is using inequalities that allow you to identify sets by making much weaker assumptions than the parametric approach, okay? So, and then there's a corresponding literature. Everything that I was just describing to you is about identification. Like how do you, if you had an infinite amount of data, how do you identify the parameter you're seeking to identify? But then there's a corresponding literature on inference. So how do you get confidence intervals for these sets? And that's actually one of the most active areas of econometrics now. And so Hito Imbens and Mansky have a paper on this, which is the technique I apply in this paper, and many others are working on this stuff. What I do in this paper is apply a similar logic to handle model uncertainty rather than missing data, right? So if you think about the problem we face here, I'm not interested in the issue that we might have statistical problems in estimating this elasticity. We do, and we talked a lot about that. But let's say we take that off the table and you've designed the ideal experiment where you have no missing data, where you estimate the epsilon hat perfectly. The problem here is that you don't know exactly what the model is that's generating that data. And so you are trying to identify this blue line, but you don't know how people are choosing within this set. And so it's a similar type of conceptual approach where you would take the extreme scenarios and derive bounds on what the underlying elasticity might be. So let's see how that works graphically. So let's say you've estimated without error that the demand curve looks like this black line here, where you're going from a price change of 1 to 1.4 is 40% price increase. You got a bunch of data and you just estimated the slope of this demand curve, right? So now you want to know, this is the observed elasticity epsilon hat. You want to know what is the potential set of blue lines, the structural elasticities that could have generated that black line that you see in the data, right? And here's how you get the bounds on that. So this is what the upper bound on the structural elasticity is going to look like, right? So look at the diagram. The idea is that the way you get the biggest possible structural elasticity is if you start at the bottom of this set and end up at the top of the second set, right? If I make the blue line any steeper, I won't be able to contain the black line within the two sets, which is the requirement that I have. So that's the largest possible structural elasticity that could have generated the data that you saw. Conversely, you can ask what's the smallest possible structural elasticity that generated the data you saw. And that picture is going to look like this. If I make the blue line any flatter here, the black line cannot be contained within the two red sets, right? Okay, so now you can do the math and solve some equations to get formulas for what those upper and lower bounds look like, which turn out that you can get an analytical formula if you take some Taylor approximations. And the Taylor approximations are what are generating this small delta statement. And it turns out that the range of structural elasticities consistent with an observed elasticity of epsilon hat, given a level of delta, is approximately given by this formula here, which I'll describe in a second. Yeah.
Can we get bound?
Okay, so the point is, you give me an epsilon hat, you tell me what level of frictions you want to allow, and then you tell me the size of the price change that you use for identification. So how big was this price gap that you used to estimate that elasticity? That's the delta log p. And these formulas map to lower and upper bounds on the structural elasticity as a function of those parameters. Okay, so the formulas look a bit messy, but let me just describe, what's the key intuition here. The point is, it's the simple mapping from these three parameters that we can specify or that we have to what the structural elasticity could be. And importantly, this is totally independent of what the underlying model might actually be, right? So think about what a dynamic adjustment cost model might look like, which is common in like the macro literature. Those are very complicated models because there are a lot of parameters that end up mattering. You need to know what the evolution, the stochastic process of the prices look like, how tastes evolve, how adjustment costs might change over time, right? So you could have like state-dependent adjustment costs and so forth. All of those things are not going to end up affecting these bounds, right? It doesn't matter what the underlying structure is, you're always going to lie within this set. One key feature of these bounds, which you can see here, is that you have a delta log p squared in the denominator. So the bounds are shrinking at a quadratic rate with the size of the price change. That turns out to be really important, as we will see in the application to labor supply. But what it means qualitatively is that the bigger price changes contain a lot more information about what the structural elasticity is than small price changes. And so this actually gives a simple principle that I think is useful in empirical work. From the perspective of maximizing statistical precision, you might think that it's useful to pool lots of small price changes, right? That's kind of the idea of the Gruber and Saez paper, where they take all tax changes over a 20-year period in order to estimate elasticities with as much precision as they can. But what this says is, from the perspective of dealing with frictions or things like inattention, you would rather have a couple of very large price changes than lots of small price changes, because those few large price changes are going to overcome these frictions and give you a lot of information about the structural elasticity. But having a dozen small price changes, each one is going to give you estimates of epsilon hat that may not correspond very well to epsilon, right? So it suggests that the technique of pooling a lot of price variation, small price variation, may not be nearly as good as finding one sharp quasi-experiment, like in that Ito paper on electricity, where he uses the spatial discontinuity. I'm not going through this in much detail, but you can read more about it in the paper. I just now want to contrast what I was showing you previously were the bounds for the intensive margin elasticity. So that was in a model where you were choosing consumption of the good continuously, right? Now I want to show you the parallel version for the extensive margin and then talk about the application to labor supply, where hopefully all of this will be clearer. So let's do the same exact exercise of figuring out the largest and smallest structural elasticities consistent with a given epsilon hat, but assume that you can only choose x as 0 or 1, whether to buy the car or not. So flow utility in that case, let's just simplify it to look like this: y plus bix, where bi denotes your taste for good x, how much you value having the car. And there's going to be a distribution of those tastes in the economy, which is going to be smooth. So remember, anytime you have an extensive margin model, you need something that's going to make the problem smooth, and that's typically taste heterogeneity. So that's going to generate a standard threshold, very simple formula here, where if your taste exceeds the price, then it's going to be optimal for you to buy. And so the fraction of people who buy is just given by 1 minus the CDF evaluated at the price, right? Let's let the structural extensive margin elasticity be denoted by eta, which is the standard definition, change in fraction buying divided by change in price. But fraction buying here is at the optimum. So theta star A minus theta star B, right? So this is what would happen in the frictionless case where everybody's optimizing. And then analogously, let's let theta denote the actual fraction of people who buy or who start working when the EITC changes and so forth. And eta hat denote the observed extensive margin elasticity. So now the exercise is going to be in parallel to the previous one. You give me an estimate of eta hat, you tell me a delta. I want to bound eta. I want to bound the structural extensive margin elasticity. And here's the key property of the extensive margin bounds. So this diagram shows you what the bounds look like. Let's focus on the red series first. So x-axis is the observed elasticity that the econometrician estimates, epsilon hat. Y-axis are the bounds on the structural elasticity. I'm assuming in this calculation delta of 1% and a price change of 20%. So, and then I'm just applying the formulas that I showed you for the intensive margin, and then a similar formula for the extensive margin. So first of all, you can see that with a 20% price change, the intensive margin bounds are incredibly wide. All right, so if you estimate an elasticity of 0.2, the true underlying elasticity could be anywhere from basically 0 or 0.01 all the way to well over 2. So what that's telling you is that the typical study that might use a 20% price change doesn't really contain that much information about what the underlying structural elasticity is, even if you allow for very small frictions. And why are the bounds so wide? It relates to the fact that the utility function looks locally flat around the optimum, right? So remember that, that picture where the costs of deviating from the optimum are second order. It's not such a big deal if the price changes by 10%, you don't do anything, because when you re-optimize the number of apples you buy, you get a small gain because you were already close to the optimum to begin with. So that feature of the problem, which is going to come out of any optimizing model, generates very wide intensive margin bounds. But here's the interesting thing. On the extensive margin, as you can see, the bounds are incredibly tight. So if you estimate an elasticity of 0.2, you basically know the structural elasticity has to be between 0.18 and 0.22. That is, there's very little deviation of the observed elasticities from the structural elasticities. Why is that? So it comes back to the second order utility costs point. On the intensive margin, the costs of not responding to a tax change, as I showed you with some examples like from TRA 86, are incredibly small because you're close to the optimum. On the extensive margin, they are very large. In fact, they're first order. That's mathematically what's going on. So let's take, so mathematically, the intuition is that on the intensive margin, the cost of not re-optimizing is proportional to the price change squared. On the extensive margin, because you are not near the optimum to begin with, the cost of not re-optimizing is proportional to the size of the price change itself linearly. And that makes the utility cost of not responding much larger and makes the bounds much tighter. Yeah? No, if you're estimating at the macro level, this still holds because the costs are borne at the micro level. It's only if you have like a representative agent model where the representative agent is choosing for all the people in the economy that it looks like an intensive margin model again. I mean, I'm happy to talk to you about this more. That's a technical thing, but you're right that if it was a macro representative agent model, it would look different, but that's not how the data is actually generated. Okay, so let me give you an intuitive verbal example of what's going on. So let's say you are looking at the EITC expansion, and you're a person who is not working prior to the Clinton EITC expansion. And let's say you were just about, you're the marginal guy, you were just about indifferent about working prior to the Clinton EITC expansion. And if you were to start working, you would have a job that would pay you $10,000, okay? So prior to the expansion, let's say for simplicity, there was no EITC. And so your disutility of working was $10,000, and your benefit from working, you'd earn $10,000 if you work. So you're just indifferent and you decide to stay out of the labor force. Now Clinton introduces, let's say, the EITC, which gives you an extra 20% subsidy if you work. So now you get an extra $2,000 if you enter the labor force at an income of $10,000 and start to work, right? So now if you work, your net gain is $12,000, but your disutility of labor is still $10,000. So you get a pretty substantial gain from entering the labor force. You get a net gain of $2,000. If you don't respond and pay attention to the EITC tax change, the expansion of the EITC on the extensive margin, you don't get that extra refund, right? You completely lose the refund because you haven't paid attention and re-optimized. So it makes sense that a lot of single women with kids figured out that you could get these big refund checks if you start to work and you see large extensive marginal elasticities around the EITC expansion, which is the Meyer and Rosenbaum paper. But now think about the same logic on the intensive margin. If I'm already working at pretty much close to my optimal hours and Clinton increases the size of the EITC, I get the extra EITC refund check even if I don't do anything and completely ignore it. I get the direct income effect without re-optimizing. The benefit of re-optimizing is I get this extra triangle, this extra second order benefit, because now I work 35 hours instead of 30 hours a week. And that ends up having the second order benefit, which is going to be much, much smaller, like 1/20th the size of the direct refund effect. So this, I think, is a useful lesson because it suggests that the reason we see very clear evidence of extensive margin responses but not intensive margin responses might have to do with frictions and the identification strategies we use rather than some deep feature of the economy which says that extensive margin responses are just much more important than intensive margin. It also fits with the EITC paper that I showed you, the differences across neighborhoods, where you actually do see that the EITC has very clear effects on the intensive margin earnings distribution when you do these steady state comparisons across places with different levels of information, but you would not pick that up when you look at the reforms, unlike on the extensive margin where you do pick it up. Okay, so that further leads me to believe that this kind of stuff is actually central in thinking about how the policies are affecting behavior. Questions? Okay, so this is just recapping what I said. The bounds on the extensive marginal elasticities shrink linearly with delta rather than in proportion to the square root of delta, which is what happens on the intensive margin. And so, the bounds end up being much tighter because of the intuition that I described. So now what I want to do, the last thing on this, is ask what can we learn about the structural elasticity from existing estimates of the labor supply elasticity. So let's take this technique and apply it to the literature on taxation and labor supply, and it's going to provide kind of a synthesis and summary of the literature that we've been talking about in the past few lectures. So we're going to take estimates from a broad range of studies that estimate intensive margin Hicksian elasticities, like the ones we talked about, and we're going to calculate bounds on the intensive margin structural elasticity, allowing for frictions of 1% of net earnings, just as an illustration. So what does that mean, by the way, just to be clear? It's allowing for the possibility that everyone in the economy is making decisions such that on average, we're sort of losing 1% of GDP every single year because of suboptimal decisions. So, we can debate whether that's a small or large number. In the end, I think what you want to do is like a sensitivity analysis as you vary delta, which I'll show you, and ask how sensitive the estimates are to varying that delta, which gives you a sense of the stability of the estimates. But that's how you interpret it. What fraction of sort of GDP is being left on the table because of suboptimal choice? Okay, so we talked a lot about these studies. I'm not going to review them here, but we talked about the McCurdy study, a bunch of taxable income estimates like the Iceland study and so forth. For each study, there's an epsilon hat, which we painstakingly calculated for all of these papers. Standard error, a size of the price change used for identification, and then you can compute the bounds, okay, using the formula that I showed you. And then there are more studies here of top incomes, and then the macro Prescott type studies that we also talked about. So it's easiest, rather than staring at this morass of numbers, let's look at this on a graph. So start with the McCurdy 81 study, right? The seminal study on life cycle labor supply and Frisch elasticities and so forth. So this is McCurdy's estimate of the Hicksian elasticity shown by the blue dot of about 0.15. And then the red interval shows you the bounds on the structural elasticity calculated the way I just described. And what you see is that they range from 0.01 to roughly 0.8. On the x-axis here is the size of the change used for identification in that study. Remember, that's the critical parameter that determines the size of these bounds. Now let's introduce all the other studies that we talked about in the literature. And I've tried to restrict to the studies that I think are decently identified and left out the ones that are doing crazy correlations. So the first thing that you can see is that the blue dots are all over the place, right? This is why public finance and labor economists, macroeconomists think that there's tremendous disagreement about what labor supply elasticities actually are, and that I think is at the root of the debate intellectually about tax policy. But here's the interesting thing. The first thing that you can see is that there are no disjoint sets in this figure. Okay, so even though there's so much dispersion across the blue dots, all the bounds are overlapping. So what that means is if you allow for small frictions of 1% of consumption, you can reconcile all these disparate elasticity estimates, even though they're from very different countries, very different subgroups, very different estimation methods. It's still the case that just allowing for small frictions, the possibility that people may not have paid attention or may not have adjusted, can perfectly well reconcile why you see this dispersion. Now, a skeptical view of that is, basically what you're saying is these bounds are super wide for every study, so none of them really contains any information, and that's why they all agree with each other. So that actually turns out not to be the case, at least with a delta of 1%. So the way you can get more information from this type of approach is similar to like in IO. The way you get more information is by combining lots of moment inequalities. So here, each study is generating bounds, and if you take it literally, you can take the intersection of all those sets to get the space where the parameter actually lies. Now, there's some complicated econometric issues once you recognize that these are actually point estimates with confidence intervals. Once you're combining all these inequalities, I don't want to get into that here, but that's like the kind of thing that Viktor Chernozhukov has been working on recently. But in any case, ignoring that problem for the moment, if you take the intersection of all these sets, you get unified bounds going from 0.47 to 0.51. And what's going on here, so like where do you get the upper bound? You have this Blau and Kahn study, which I described, which uses the grouping estimator. The grouping estimator generates very large wage changes because over the past few decades, it's not just about tax policy. There have been really differential wage trends across these groups. And if you believe their research design, that gives you a point estimate, but it also gives you a very tight upper and lower bound because it's got so much information. The idea is that if you have doubling of wages or halving of wages, people would probably start to pay attention to these things, right? That's basically the logic. Yeah.
So the bounds that are shown there, that's just taking the smallest upper bound.
Exactly. It's the least upper bound and the largest lower bound. That's the idea. Yep. Okay, so then you can repeat this exercise excluding studies that you think might have suspicious identification, like macro studies and the top income studies, which as we talked about, my sense is the top income studies are actually estimating a different elasticity, the intertemporal shifting, rather than a real labor supply effect. So I want to leave those out as well. So of course, when you exclude information, you're going to get wider bounds, right? So you get from 0.28 to 0.54. This is what I think a plausible range is for the intensive margin Hicksian elasticity for actual labor supply. And then it's natural to ask, why do you pick a delta of 1%? How do you know that's the right number? We don't. So it's natural to say, how did those unified bounds vary as you vary delta? And so that's what this diagram shows you. So delta on the x-axis, I showed you the bounds with the delta of 1%, which range from 0.28 to 0.54. And then we just vary the delta. So two things to notice here. First, if you let delta fall below 0.5, you no longer get the unified bounds because the sets are no longer intersecting. So we know that if you have a delta of 0, these point estimates are all different from each other. And what this is telling you is you need to allow a delta of at least 0.5% in order to explain all the different estimates across the 30 studies. So I find that number to be a useful statistic in its own right, because you can think of it as kind of a measure of the economic significance of the differences between all the estimates in a literature. So you could imagine doing the same thing for other literatures where you have lots of different estimates, and you can ask, is it because they are actually estimating fundamentally different parameters, or is it just that small frictions could explain the differences that we see? And what this is telling you is that in the labor supply literature, at least, given the type of evidence we have to date, small frictions are enough to explain what's going on. Delta 0.5% doesn't seem that large. At that minimum delta, you can get an estimate, a point estimate of what the elasticity would be, and that ends up being 0.33. So if you want to pick one number adjusted for these imperfections, that gives you 1 point estimate. Okay, so then you can go to the other extreme and ask, of course, as you make delta bigger and bigger, these bounds are going to get arbitrarily wide, right? I, just based on introspection, think that a delta of 5% seems relatively large. That is, coming back to what I was saying earlier, people are leaving 5% of consumption on the table every single year on average by making mistakes in labor supply choice. That seems like a lot. And so what I want to point out is that even with a delta of 5%, which seems quite large, you still get somewhat informative bounds on the Hicksian elasticity. In particular, you can rule out elasticities well above 1, and below like 0.15. And that actually rules out some parameters that people use in the literature, like macro models are sometimes calibrated with elasticities well above 1. And what this says is, whatever you think about frictions, given all the available data, it is very unlikely that the true elasticity is above 1. You can't appeal to this as an explanation for large elasticities. Okay, so the next thing that I want to talk about before coming back to this curvature point is coming back to the question that motivated this sort of exercise, which is asking whether frictions can explain the gap between micro and macro elasticities, or what exactly is driving the gap between micro and macro elasticities. So in this macro annual paper, we collect a bunch of estimates of intensive and extensive marginal elasticities, adjust the intensive margin ones for frictions like the way I described, and then evaluate the macro prediction. So there are two key lessons here. The first is that you can basically match the macro facts on cross-country labor supply with the micro estimates once you account for frictions and account for the extensive margin. So this is the scatter plot I showed you before from Prescott. The green line is Prescott's best fit line. That's the best fit line to these data. The red line shows you the projection from our preferred estimate aggregating all the micro evidence of the intensive and extensive margin elasticities. So the way I look at this is not that this is the regression you want to run to actually identify the elasticity, because there are lots of differences across these points, but rather that you can, this dispersion of hours of work across these countries is not that puzzling given the micro evidence once you account for these factors. And so in particular, what's going on is, although micro estimates of intensive marginal elasticities are very close to 0 if you don't account for frictions, I think once you adjust for the frictions, you get a number like 0.33, which is what I was describing before, which is in line with the Prescott intensive marginal elasticity implied by the macro data. On the extensive margin, I'm just taking the mean of micro estimates. It's not totally clear that that's right. You want to take some weighted average across subgroups, which is complicated. But the point is, there are lots of extensive margin micro elasticity estimates which are around 0.2 without doing any adjustment, which makes sense as I was talking about with the example of frictions. The macro implied elasticity, comparing employment rates across countries with different average tax rates, is also around 0.2. So this actually matches fairly decently. My guess is that all of these elasticities are probably somewhat upward biased because of publication bias. So, I'm taking the elasticities as given as reported in the literature, right, and then applying these techniques. But, a very clear pattern you see is that if you have, there's like a clustering of t-statistics around 2 and all kinds of other fishy things. So my guess is, people have chosen specifications that shade these up a little bit. And so probably like the aggregate elasticity is less than 0.5 intensive marginal elasticity, might be a bit less than 0.3. But in any case, it doesn't seem like there's a huge puzzle to be resolved there. Things look very different on so this was for the Hicksian, right, cross-country. Things look very different when you're trying to explain the business cycle fluctuations with the Frisch elasticity. And so this graph shows you that. So the blue line shows you employment fluctuations over the business cycle detrended, as I was describing in the last lecture. The red line, again, shows you the micro prediction, where we multiply the real wage series by our preferred estimate of the micro extensive Frisch elasticity. Remember, these are employment rates, so we're trying to match the extensive margin. And what do you see here? The amplitude of the fluctuations implied by the micro data are dramatically smaller than the macro data. You don't come anywhere close, okay? And so what, in my view, is the key remaining puzzle is this. There's some, like a limited amount of evidence on the intensive margin Frisch elasticity. I'm not sure if we're way off there. It's not totally clear. But where we're clearly way off is this red box here, where the micro estimates seem like 1/10 as large as the macro estimates, and frictions are not going to explain that, or not optimization frictions at least. And so the key lesson of this is, even if you have indivisible labor, even if you account for the frictions, a Frisch elasticity of aggregate hours of more than 1, which is what you need to explain the dramatic fluctuations in hours over the business cycle, in an RBC model, in a real business cycle model, is inconsistent with microevidence. What's like a layman's way to say that? Lots of people, we don't have 20 million people who are not working in the US today because they're unhappy that wages fell by a couple percent and decided not to work. That's what the RBC model is, right? You're on the labor supply curve. You have decided wages fell by a little bit. For some reason, we're less productive right now. And unemployment is totally explained by the fact that a bunch of people chose not to work given current wages. So if you think about it intuitively, that doesn't seem very plausible. And this is basically saying that that's the case. These people might actually like to work at the current wage, even though it's a little bit lower, but they're not able to find jobs for some reason. That it's a disequilibrium model, right? And so that's like the current modern macro literature. Rob Scheimer, Bob Hall, and many others working on these models of search theoretic models with labor wedges that might provide one solution. So that's pretty much it on labor supply elasticities. I want to make two other points that tie back to the optimal tax literature, and then we'll move on. So we've talked at length about labor supply elasticities because they're central for the tax policy, the theory of optimal income taxation that we previously talked about, because they determine efficiency costs, right? But we also talked about how optimal income taxes depend upon the benefits of redistribution and not just the efficiency costs. What are the benefits determined by? Well, they're determined by your social marginal welfare weights, but we think those marginal welfare weights, one of the critical determinants of those is the curvature of the utility function. That is, how much does the marginal utility of consumption diminish as people have more money? So intuitively, what's one of the key factors in determining if I want to take money from a guy who's earning $200,000 and give it to a guy who's earning $20,000? It's whether the marginal utility of consumption is lower for the guy who's earning $200,000 relative to the guy who's earning $20,000, right? So as a result, the curvature of U of C, the utility function over consumption, typically measured by the coefficient of relative risk aversion, the second derivative divided by the elasticity of the marginal utility of consumption with respect to consumption. That's what this is. That determines the answer to the question that I just described. That risk aversion parameter, which I'm going to call gamma, is also central for the social insurance literature that we're going to talk about next, and for the calibration of macro models. Now, it turns out that the literature on labor supply actually contains quite a bit of information about this gamma parameter that we're also interested in measuring. And so you can get all of the inputs that you're interested in at some level for optimal tax from the labor supply data itself, which is a useful property. So there are a few papers in the macro literature, a very well-known paper by King, Plosser, and Ribello on the structure of utility functions and elasticities. And I'm going to talk briefly about this 2006 the paper. This is the one in the AER. So let me first give you the simple intuition and then just go through a quick derivation. So let's suppose that risk aversion, or the curvature of utility, is very high. So the marginal utility of consumption actually diminishes very quickly in practice, right? So that is, the utility function looks like this rather than something that's much more linear. Okay, so this is the high gamma case. So suppose you're in that world. So what should we see when we look at labor supply, look at data on labor supply? As wages rise, we see with this utility function that people quickly become sated with goods, right? So look at the way I've drawn this. As your wage goes up and you have more and more consumption, you basically reach a point where the additional dollar is not worth that much to you. And so what should you opt to do as you have higher and higher wages? You should choose to consume more leisure, that is, work less, rather than continue to work a lot as your wages are going up, right? If your utility function is very curved, at some point you should basically say it's not worth it anymore. I'm going to switch to part-time or whatever. But what would that imply? This is a statement about the uncompensated elasticity. It would say that as wages go up, we should see labor supply falling because people are trying to hit this target level of earnings where they become sated with goods and don't really want to go beyond that. Those of you who are taking like a psychology and economics class will also notice there's a connection to the reference-dependent models of utility where you're going to get the similar property where at some point you don't want to go any further and then you end up working less as wages go up. Okay, so take the extreme case. If the marginal utility of consumption drops to 0, then the agent's going to reduce labor supply 1-to-1 as wages go up. So if I raise your wage by 10%, you're going to work 10% less because you're going to say, I don't need money beyond 100,000 or whatever. Okay, so people do not behave like that in practice in the data. When you raise wages, they tend to work more, or to take an extreme bound, if anything, maybe they reduce labor supply with an elasticity of 0.1, but that's actually being generous. So that places an upper bound on the size of gamma, as you can see based on this logic. Because if the utility function were really curved, I would see this elasticity being very negative. And so the fact that it's not that negative means that gamma can't be that large. That's basically the idea of the paper. So let's just see how it works mathematically. This technique turns out, this is an identity that turns out to be useful in many applications if you're doing theoretical work in public finance. So let's let Y denote your unearned income, W your wage, L your labor supply, and U of C comma L your utility function. At an interior optimum, we know that you have this usual first order condition. Just assume a static model here, that everything works in a dynamic model, which is what's shown in the paper. So L has to satisfy this condition here where the marginal utility of earning $1 more, which is given by the wage times the marginal utility of consumption, equals the marginal disutility of supplying that 1 more hour of labor. Standard condition. Now look at the comparative statics of that condition. In particular, think about 2 experiments. Suppose I randomly give you more cash. So that's the income elasticity experiment, like the Hito and Rubens Hasserdote paper. And think about an experiment where I vary your wage, holding your total income fixed, so I estimate the compensated elasticity. You can implicitly differentiate this equation with respect to Y and with respect to W to get what those 2 derivatives look like. You do some algebra, and you end up getting an equation that looks like this, which is a formula that connects the labor supply elasticities that you're able to estimate in the data that we've talked a lot about, income effect and substitution effect, directly to the curvature parameter that you're interested in. Okay? So there's a tight link between the ratio of the income effect to the substitution effect and the degree of risk aversion. So it's like what I was describing before. The bigger our income effects relative to substitution effects, the more curved the utility function has to be. So let's now go through that a little bit with a little bit more detail. So let's take an example where we assume that the person has no unearned income, Y equals 0, okay? And at the initial wage, W naught, the agent works L naught hours. Let's consider the effect of increasing the wage by 1% to some level W1. What is that going to do? It's going to do 2 things. Let's look at this graphically. So what does this graph show? It plots the marginal utility of consumption versus labor supply. Why is that downward sloping? The more you work, the more consumption you have diminishing marginal utility. Okay, that comes from the fact that the utility function is concave. Then you have the marginal disutility of labor. So that's an upward sloping function. That's because we assume that the marginal utility of supplying labor has a convex, there's a convex cost, right? So that's an upward sloping function. The way you choose your labor supply is by working, the optimality condition is that you choose the point that where these 2 intersect. So at a wage of W naught, you are going to supply L naught units of labor. Okay, so now I'm considering this experiment where I raise W naught by 1%, all right? So I'm raising it to W1. What are the effects on this marginal utility schedule? First, you see that there's a W multiplying the marginal utility, right? So that's going up by 1%. So this thing is going to shift out by 1% to the blue curve. It's just a direct effect. That's actually what's driving the substitution effect. That is exactly what drives the price effect of labor supply. The value of working an extra hour has now gone up, so you want to work more. But there's also a second effect, which is when you have a higher wage in here, the marginal utility of consumption is going to fall, and this is due to the income effect. You have more consumption, so the marginal value of working an extra hour is now lower as a result of the second effect. And the extent to which it's lower is actually exactly what gamma is. Gamma measures the impact of increases in income on the marginal utility of consumption. And so the net effect, so the income effect, the gamma effect pulls you back this way. And if gamma is above 1, then you're going to end up to the lower side here, where increasing the wage ends up reducing your labor supply. And if gamma is less than 1, then you stay on the other side, where you have a positive uncompensated labor supply elasticity. So you can see from this diagram where the key result that's going to come out of this when you connect it to the data is basically that you cannot have a gamma much above 1. Risk aversion cannot be much above 1, otherwise you'd see patterns in labor supply that are totally disconnected from the data. There's another technical issue, which I won't get into a lot of detail on here, which is that this other curve, which is the marginal disutility of labor, can also be moving around as you change the wage. And basically what I show in the paper is you can bound the extent to which that thing is moving around, and that's not very big, so it's not a big deal. But that also turns out to be technically very important because it relates to this issue of ordinality versus cardinality. So risk aversion is a cardinal property of the utility function. That is, when you transform that utility function, like let's say you square it, you're going to get a different number for risk aversion. But when you square the utility function, you're not going to change labor supply elasticities, because labor supply elasticities, labor supply is an ordinal, it's ordinal data. It doesn't matter what the cardinality of the utility function is. So all this stuff is a bit technical and a bit of an aside, but you need to pin down the cardinality of the utility function, and the way you do that has to do with pinning down this complementarity parameter, which is what that other curve shifting is about. So if you guys are interested in more of that stuff, you can look at the paper, and I'm happy to talk about it later. All right, so getting back to the main point here, the idea is that, again, now you have this formula, right? So you give me an estimate of the income elasticity, you give me an estimate of the compensated wage elasticity. Again, I take this usual set of studies, and then I can calculate an estimate of gamma under a couple of different assumptions about that complementarity. And basically, exactly as I was predicting, across all of these studies, no matter what estimates you use, those elasticities hover around 1, basically. And the fundamental reason is nobody finds massive income effects relative to substitution effects. And that is a useful property because what it justifies basically is writing down a log utility function. It says that a log C utility function is a pretty decent approximation and is consistent with the labor supply data, which is useful for pinning down optimal income taxes and various other things. Okay, and so then we'll see, how this formula actually ends up being applied in a bunch of other stuff that we'll talk about. All right, so last thing that I want to talk about in the tax topic. So think about it like at an abstract level. We've covered evidence essentially on 2 of the 3 elements critical for optimal income taxation. A lot of time on labor supply elasticities, some time on the measurement of preferences. I think there's actually a lot more to be done on figuring out how all these reduced form elasticities we estimate map to preference parameters. This is one illustration of that, but people, I think, don't do that nearly as much as we could. And then the third thing is, if you think back to the Saez optimal income tax formulas, you need to know what the income distribution actually looks like, right? We talked about one example of that, like the Pareto tail at the very top with a Pareto parameter, tail parameter of 2, right? But I just want to show you that the third piece can also be well measured using tax data, even for very high incomes. And so this is the very well-known work of Piketty and Saez on top income inequality, which is of interest in its own right, but is also of interest in connection with calibrating optimal income tax models. So Take the Saez 2004 paper. There are now a bunch of studies like this. He compares the top 1% relative to the bottom 99%. And he's just looking using tax data on publicly available tax data, actually, on at the time series trends for these two groups. So for the bottom 99%, real income increases up to the early 70s and then pretty much stagnates since then. We know that from other work. The top 1%, which is what's the innovation in this recent work? It's that you have enough data from publicly released tax record information that you can actually understand what the very upper tail looks like. Traditionally, studies of inequality were based on things like the CPS or the PSID, where you just don't have enough guys who are making, however many X million dollars in the CPS, right? And the thing is top coded, more importantly. Here, you can actually figure out from statistics of income public use samples what the upper tail, they put out these tables that tell you these cutoffs. So let me show you two graphs. So this is the evolution of average income for people in the bottom 99%, shown by the black series, and the average marginal tax rates for that group. So this is what I was saying. You see it going up, then it's kind of flat. Marginal tax rates go up and then down a bit. You just look at those time series patterns. Maybe there's a relationship, maybe there's not, but it certainly doesn't jump out at you. Look at the top 1%, and this is the phenomenon you read a lot about in the newspaper. It's pretty much flat, and then it just shoots up average incomes for people in the top 1% and has continued to go up dramatically, actually, in the 2000s. And this is the tax series for that group, and you can see it's right around TRA 86 that this really takes off. Now, what's interesting, and I think what we don't really know the answer to, like this immediate change to me it's consistent with the Feldstein, Gouldsby, and all that kind of work, suggesting that there was some immediate short-run response, some of which was probably shifting across bases. Remember, shifting of corporate income into the personal income tax base is going to do that. But then why does it continue to go up after that? That's, of course, one of the very interesting questions that we don't really know the answer to. One concern potentially is that some of what you're picking up here is a reporting base shifting effect rather than an actual increase in the amount of money top income individuals have. But I think that that's almost certainly not most of it even. Any questions? Okay, so that is all we're going to talk about on labor supply and income taxes.